Hi everyone, my name is Ari and I'm a PhD student at the University of Münster in Germany. And today I want to present our recent results in the area of automatic performance tuning, or auto tuning in short, especially regarding the tuning of so-called interdependent tuning parameters, all based on our auto tuning framework ATF. Yeah, before we start, so just that you're prepared, so this talk will be actually on a quite high level, which means we will focus on discussing in detail what we are doing and why we are doing the things. And we address the whole questions by illustrating our basic ideas only. And details about our approach can be found in the paper. So if this talk can raise your interest, please check them there. So the first thing we should clarify is, so what is for us actually auto-tuning, or how do we look at auto-tuning in this work? And in this work, auto-tuning means automatically identifying the values of so-called performance critical parameters, like for example, the sizes of tiles or numbers of threads. And for this, we assume an already implemented generic code generation approach, which is a generic optimization process based on optimization parameters. And auto-tuning aims at identifying optimized values of these kind of parameters. So an auto-tuning usually consists or works in three major phases. This is the generation, storing, and the exploration of the program-specific search space. And in the first phase, we start from a set of optimization parameters, to which we also refer as tuning parameters in the following. And these are usually identified by their name and the range of possible values. And in the generation phase, starting from this set of optimization parameters, we generate the set of all possible valid parameter configurations, which are in the easiest case all possible combination of parameters values. And in the second step, in the storing phase, we take this parameter configuration and we store them in some kind of data structure. So in the easiest case, this can be a one-dimensional array. And in the last step, this data structure is explored usually by using numerical search techniques like hill climbers or genetic algorithms or the like, or even machine learning based approaches, so that we obtain finally a well-performing configuration. And auto-tuning can be categorized in two major categories. We have special purpose auto-tuning on the one side, and we have general purpose auto-tuning on the other side. And the basic idea in special purpose auto-tuning is that the auto-tuner is specifically designed and tied for the code you actually want to emphasize, we want to auto-tune. And a notable example of such approaches are, for example, the Atlas library for linear algebra routines. I think this is one of the most popular examples. But you have also Patios for stencil computations, FFTW for fast Fourier transformations, and so on and so forth. In contrast, the basic idea in general purpose auto-tuning is that the general purpose framework automatically generates a special purpose auto-tuner for the user based on some simple high-level information, like for example, the parameters name and their ranges. And a notable example of general purpose auto-tuning approaches are, for example, OpenTuner. This is from Professor Saman's group at MIT. But we have also kernel tuner and lib tuning and classical approaches like active harmony and Oreo. And we're now briefly comparing the advantages or disadvantages of special purpose auto-tuning versus general purpose auto-tuning. So special purpose auto-tuners usually achieve quite good tuning results, and this because they're specifically designed and optimized towards the application that we want to optimize. However, they have to be designed and implemented from scratch for each new target application, which requires, of course, expert knowledge and is also cumbersome for the user. On the other hand, we have general purpose auto-tuning, and general purpose auto-tuners are actually very convenient to use because they automatically generate a special purpose auto-tuner for us, for the user. However, the current approaches struggle with programs that have these so-called interdependent tuning parameters. And now, what are these interdependent tuning parameters? And here we can see first on the left side, the classic example of independent parameters. So this was the most common example for application that we have seen so far. And independent parameters actually means that each combination of parameters values represents a valid configuration in the search space. Now, when we look at interdependent parameters, they're only combinations that satisfy a set of constraints represent valid configurations. And if you look, for example, at quite recent architecture, like, for example, GPUs, which have a complex core memory hierarchy, then we usually want to tune tile sizes on different memory layers. And of course, the tile size on the lower layer has to be smaller than or equal to a tile size on an upper layer, because the lower layer tile is only a chunk of the upper layer tile. And these constraints have to be satisfied so that inserted the configuration in the code, in our actual program code, leads to correct program behavior. And now, how are interdependent tuning parameters handled in the current general purpose auto-tuning approaches? So we have on the one side approaches that have no support at all for the interdependent parameters. So invalid configuration are just kept in the search space, and this severely hinders the tuners from finding well-performing configurations, as we will show at the end of this talk. And we have on the other side approaches that support these interdependent parameters, but have only limited efficiency because of suboptimal processes to generating, storing, and exploring the search space of these interdependent parameters. And yeah, this is actually exactly where our work aims to start. So we present 3 new contributions of our general purpose auto-tuning framework ATF, which aim to address exactly the weaknesses of special purpose auto-tuning approaches for programs with interdependent tuning parameters. So in particular, we show that ATF generates a search space of interdependent parameters with very high performance. ATF stores such spaces with a low memory footprint, and ATF explores these spaces efficiently. So we aim to contribute to each particular phase of the auto-tuning process for programs with interdependent tuning parameters. And our 3 contributions are mainly based on 2 novel concepts. These are the concepts of parameter constraints and a novel chain of tree structure for representing the spaces of interdependent parameters. So now, just quite briefly, our basic idea to our contributions regarding the particular phases. So regarding the generation phase, so our ATF framework relies on parameter constraints, and the parameter constraints checks constraints on individual parameters, while the traditional search space constraints, which are used by the related approaches, checks full configurations. And this may be a simple design difference, but it's very significant because this design difference enables checking constraints early in the generation process. It enables generating the groups of interdependent parameters independently of each other and also in parallel. And we can also generate individual groups in parallel. Then regarding our storing phase, so ATF search space structure, this chain of tree structure, avoids memory-intensive redundancy that we usually have in the traditional one-dimensional search space representation. So this enables actually implementing important applications in the memory limitations of current state-of-the-art systems. And regarding the exploration phase, our novel chain of tree search space representation allows to be naturally mapped to a multidimensional coordinate space. And the multidimensional coordinate space is actually the most efficient structure for most kinds of search techniques, especially the numerical ones. And thereby we have reduced the complexity of exploring a search space to just exploring a coordinate space. And for these kind of spaces, actually a bunch of existing approaches achieve quite encouraging results already. So now regarding our experimental evaluation, so we have a quite extensive experimental evaluation in our paper, I would say. And here we just present some highlights. And what we want to show is that ATF is able to auto-tune important applications that target both CPU and GPU on real data sets to high performance. And what you can see here is that ATF is able to auto-tune the implementations to even higher performance and hand-optimized approaches. For example, Intel MKN or NVIDIA QBLAS, which are specifically hand-optimized approaches for linear algebra routines on Intel architecture and NVIDIA architecture correspondingly. And we can also achieve better results with our auto-tuned implementations than MKLDNN or NVIDIA QDNN. And especially also, in particular, compared to other auto-tuning approaches, like, for example, CL-Tune, we can sometimes achieve better performance by even orders of magnitude. So if this is interesting for you, please check the details in the paper. So there are a lot of experiments, and these are, as I said, just some highlights. So now just very briefly, one slide so that you have at least one theme, the user interface of ATF. So actually the user interface was the focus of our previous work. And this is just very briefly summarized here on one slide. And if you want to use ATF, what do we have to do? So we take our code that we actually want to auto-tune, and we have to annotate this code by, I would say, easy to use tuning directives. And the directives specify, for example, the tuning parameters by their names and range of possible values, and of course also their constraints. And then ATF automatically generates a special purpose auto-tuner that is specifically optimized and tied to our particular application. Yeah, this is actually the end of my talk. So thanks a lot for listening. And I would be very happy to answer some questions now. And of course, every time via email. Thank you.